Hello everyone. In a previous paper, Shulkov et al. Proposed an approximate representation of a possibly multidimensional random variable x that allows for an easy computation of the representation of a random variable f of x for any given function f. In this paper, we complement their idea with general theoretical convergence guarantees on the representation of f of x given convergence guarantees on the representation of x. Concretely, we represent a random variable x by a collection of weighted sample points wi, xi. To compute the representation of f of x, we simply apply f to each sample point xi. Now, how do we get the weights and the sample points for the representation of x? Well, we are free to choose any method we like. The price for this freedom is that we need to quantify how good or bad our representation is. And to do so, we map each random variable and each representation to a function in a reproducing kernel Hilbert space, or AKHS. We then define the distance between a random variable and its representation as the distance between the images in the AKHS. Now, concerning our results, we prove that in these AKHS, if the representation of x converges to x with growing sample size, then the representation of f of x converges to f of x. We also provide finite sample guarantees when using Matern kernels. Once again, the strengths of these results are that they do not assume anything on how the representation of x was constructed. This allows, for example, for the following application. Imagine we want to compute the representation of f of xy, where f is now a function of two independent random variables, x and y. Given n sample points from x and n sample points from y, we would get a representation of f of xy with n squared points, which may lead to prohibitive memory costs. Instead, we could now construct new weighted sample points to represent x and y with less points while controlling the distance between these new representations and the old ones. f of xy is then represented by much less points, and our theorems guarantee that if the new representations of x and y are still asymptotically close to x and y, then the new representation of f of xy will also be asymptotically close to f of xy. Possible future applications range from probabilistic programming to privacy-preserving data analysis.